From the waters of the Yangtze River in China rises the biggest concrete structure on the planet. The Three Gorges Dam is over 2 kilometers long and 60 stories tall. It has taken 40,000 workers over 17 years to build. When it fully comes online, this one dam will produce over 20,000 megawatts of power, twice as much as all the nuclear power stations in Britain put together. It is the pinnacle of dam engineering. The Three Gorges Dam owes its success to 5 landmark dams. At the heart of each lies a major technological innovation that allowed engineers to build ever bigger dams. One by one, traveling up the scale, we'll reveal the incredible stories behind these structures. And the inventions that allowed them to produce ever more power. 6 ingenious leaps forward, from big to bigger, into the world's biggest. China is one of the fastest growing economies on Earth. To fuel the need of its ever-accelerating industry, the nation needs more power. Much of this will be provided by an enormous dam spanning the mighty Yangtze River in central China, called the Three Gorges Dam. Our cameras have been granted privileged access to capture this amazing feat of engineering in its full glory. Before they could start building the Three Gorges Dam, the Chinese first had to divert the Yangtze River, which is almost 2 kilometers wide, and move over 1 million people from the area about to be flooded.
The Three Gorges Dam is the biggest hydroelectric project in the world. This dam used 28 million cubic meters of concrete. Maybe one way to look at it is to say it's a solid pipe of concrete, 1 meter diameter, right around the world. It's a lot of concrete.
But the Chinese authorities think it's worth the effort, as the Three Gorges Dam will provide clean and cheap electric power to millions of people. To understand how the Three Gorges Dam can produce so much power, we need to travel back in time to 19th century Britain and a modest stream in Northumberland, the power behind the world's first hydroelectric dam. In the 1800s, while Britain is at the heart of the Industrial Revolution, this house is the last word in modern living. It belongs to Lord Armstrong, an entrepreneur and obsessive inventor. He has fitted his house with state-of-the-art technology, including central heating and mechanical devices that drive elevators, laundry machines, and roasting spits. But there is one place in the house where modern technology is sadly lacking, as historian Anthony Burton explains.
This was Armstrong's real pride and joy. The picture gallery full of wonderful Victorian paintings. Bit gloomy even in daylight, but what he really wanted to do was to bring his guests here in the evening, but by the flicker of candlelight, nothing really worked.
What Armstrong needs are electric lights and a way to power them.
How do you generate electricity? Well, that's something that was known for 50 years because Michael Faraday had given the secret. You move a magnet in relation to a coil of wire. I've got a little setup here to show how it might work. Now, here we are. Here we've got two magnets on the end of this disc, and right here is a coil of wire. Now, if I make this spin in relation to that, we should make electricity. And yes, we're getting a reading on the ammeter. We are definitely making electricity.
Every time the magnets on the disc move past the coil, they generate a tiny electric pulse in the copper wire.
To make a lot of electricity, you need much bigger kit, and this is what Armstrong bought, the Thomson Vortex turbine, a grand piece of equipment.
The Thomson turbine needs a huge volume of fast-flowing water to drive the rotor. All Lord Armstrong has available is a tiny stream trickling through his estate.
What he needed was this, a lot of water. And how does he get this out of a small stream? He built a dam.
Armstrong builds an earth wall nearly 10 meters high, which turns his stream into a deep lake. This mass of water pushing down increases the pressure at lower depth. Armstrong channels this high-pressure water down through a pipe to the bottom of his dam. Here he injects it into a Thomson turbine, where the torrent spins the rotor. This in turn rotates a shaft linked to a generator that produces 4,000 watts of electricity. For Armstrong, this is only the first step to enlightenment. Now he needs to get the electricity from the turbine house at the bottom of his dam all the way to his picture gallery over 1 kilometer away. Armstrong connects 2 strands of thick copper wire to the generator to carry the electricity up to his mansion. All in all, he uses 5 tons of copper to power a single light bulb. But he has created a world first. A house lit by the power of water. On the other side of the planet in central China, the Three Gorges Dam takes Lord Armstrong's concept to the extreme. British engineer Robin Charlwood has been working on the dam since 2003 and is still impressed by its scale.
We're in one of the 3 very large powerhouses of the Three Gorges project. In this 700-meter-long room here, you can see 14 of the large turbine generators. Then beyond this one, 1 kilometer away, is the second powerhouse, and then beyond that one is yet another powerhouse which will be underground in the rock on the far side of the river. Each one of these generators cost about $50 million, to give you an idea of the scale of this project.
Debden Dam had 1 generator. Three Gorges has 32. Together they produce 5 million times more power than Debden. To drive them, the Chinese have harnessed the power of the mighty Yangtze River. In the reservoir behind the dam, the river now rises up to 60 stories above the riverbed. The water is channeled down gigantic concrete tubes towards the generators. Here, the torrent of water hits the turbines and makes them spin. This motion is in turn transferred to the rotor of the generator. This is fitted with massive magnets, which move past copper coils in the casing to generate electricity. Just one of these machines makes as much electricity as a small nuclear power plant. All 32 generators together produce enough power for 60 million Chinese.
This project is setting a new benchmark in the international hydroelectric industry. It's almost twice the size of the next largest project, Itaipu in Brazil. And of course, it's only the first of a whole series of megadams that are under construction here in China.
Back in 1878, Debden Dam showed that even the smallest stream can be harnessed to produce electricity. But to generate power on a larger scale, engineers had to wrestle with bigger rivers. To build a dam that could produce 128 megawatts, French engineers had to persuade the raging Dordogne River to run a new course. France in 1914. The outbreak of the First World War plunges the country into a deep energy crisis. With their coal fields occupied by the Germans, the French are forced to import coal from abroad to feed their power plants and keep the country going. So after the war, they decide to boost the nation's power supply with electricity from a hydroelectric dam. But building a concrete dam in the fast-flowing Dordogne River presents quite a challenge.
And this is our mighty River Dordogne here on the beach. Now, you can't just pour concrete into the middle of a river. They wanted their dam here, but in order to get one dam, they had to build three. First of all, a temporary dam goes in here, what's called a cofferdam. That stops the river flowing. You can't just stop it, it's going to go over the top unless you do something different, which is build a diversion channel right round there, and then to stop it backing back up again, you put in a second cofferdam here, and you've got a space in between which you can drain, and it's there that you can build your main dam.
At the Dordogne, engineers blast two tunnels through the rock to carry the diverted river. They drop steel cages containing rocks into the river to make their temporary cofferdam. Then they strengthen it with concrete. Now, as the river behind the dam begins to rise, it drains through the tunnels. To stop this water from backing up, the engineers build a second cofferdam. Once the water drains from the riverbed between the dams, it leaves a perfect dry spot to build the main dam.
Fortunately for the engineers, they discovered when they emptied the central part that actually the riverbed was solid rock. They could build straight on top of it.
Layer by layer, the giant concrete structure rises 30 stories up from the riverbed. The engineers then close the diversion tunnels and allow the reservoir to fill up and submerge the cofferdams. Their job done. Finally, they can open the gates to the turbines and start producing electricity. When the Gorges Dam is finished, it produces 128 megawatts, enough to help power a train line to Orléans and supply the city of Paris 400 kilometers away with electricity. The Yangtze River is over 6,000 kilometers long and in places several kilometers wide, the biggest river in China. It presents enormous logistical challenges to the dam engineers. As the Yangtze rises behind the Three Gorges Dam, it will flood over 150,000 acres of land along its banks. So the Chinese have to relocate over 1 million people from the land behind the dam. Thousands of new houses have to be built for the displaced citizens to live in. Then the engineers can begin to dam the river.
We're standing here among some of the rocks and these precast concrete blocks that were used to create the cofferdams to control the river during the construction of the Three Gorges project. Controlling the river to allow the construction of this huge project was clearly a major undertaking. I mean, the Yangtze River is one of the largest rivers in the world, very fast, very deep. So building these cofferdams and to allow a safe construction was a major operation. The Chinese claimed that this was the largest and most difficult diversion ever undertaken for a hydroelectric project, and you look at the scale of it, they were absolutely right. This was huge.
The engineers begin work on a series of stone cofferdams to block off part of the Yangtze, whilst leaving a channel open for the rest of the river to flow through. They build the first 2 sections of the main dam on the dry riverbed. Then they dump tons of earth into the river, and on top of it build another cofferdam, this time from concrete. With the river held in check behind it, they can finally build the last section of the dam. Then they must remove the cofferdams so that water can flow through the turbines of the main dam.
Having built such substantial cofferdam structures, it's a major challenge how to remove these things. So in the earlier stages, where they were built of very large rocks like this, then that could be handled with big excavator equipment, relatively conventional. But in the final stage, where they had a solid concrete wall to remove, this required some serious innovation.
Unlike the cofferdam in Gorges, the Chinese version is too tall to simply leave it in place. So the Chinese engineers build it leaving holes for explosive charges. On the 6th of June 2006, they filled them with 190 tons of dynamite and hold their breath. What has taken months to build takes only seconds to destroy. As the cofferdam crumbles, it unleashes the water stored behind it. It's the final test for the Three Gorges Dam, and it holds. Back in 1935, the Gorges Dam proved that engineers could divert rivers to build powerful dams. But to break through the 1,000 megawatt mark, American engineers building the Hoover Dam had to take their building material to the limit. In In the 1930s, the USA decided to tackle one of their big economic problems. The cities in the western United States can't grow because they lack both water and power. So to break the deadlock, engineers begin work on the world's biggest dam, the Hoover Dam.
People who worked on it were real, adventurers. There were these guys called high scalers, and they would sit on a plank hung from a rope off the top of the cliff, and they would go along with hydraulic hammers, basically smashing out the cliff face so that when you poured the concrete up to it, it would fit together well.
They poured more concrete on this dam than on any other construction project before it. But managing so much concrete can be a big headache for a dam engineer.
When you're doing really big concrete pours, there's a very particular problem, and that problem is heat. The first thing you have to understand is that concrete is made up of three basic ingredients. First of all, you have this stuff, which is cement. Now, that's the active ingredient. That's what reacts and changes. You have water, which reacts with the cement. And you have this stuff down here, which is aggregate, which is basically stone, in this case sand, which gives the whole mix its strength. Now, when we put this cement in here, what we're going to have is a chemical reaction, a hydration reaction, in fact, and it's exothermic, which means that the temperature of this lot should rise. So let's have a test and see if we're right. Oh, we can see it rising there, and it's already gone up to 15 degrees C, and if we wait around a little while longer, it'll go up some more. What we've seen there is that we do get a temperature rise. It's not much, but actually, when you're in the middle of a great big concrete pour, that heat has got nowhere to go. And so the inside of the lump of concrete gets hotter and hotter and hotter and expands. When it expands, it cracks the concrete that's on the outside of it. And if you're doing a big concrete pour in a dam, cracks are a very bad thing.
If the concrete of the Hoover Dam is poured in one go, the concrete on the outside will cool and harden first, while in the core of the dam, the concrete stays hot and tries to expand. This could stress the concrete and make it crack. So the engineers cast the concrete for the Hoover Dam in small individual blocks. As the concrete in each block cools, it shrinks, but it doesn't crack. The contraction leaves small gaps between the blocks, which engineers must fill with cement. But this clever design doesn't solve all the problems.
The Hoover Dam is enormous. I mean, there are 6 million tons of concrete in the Hoover Dam. And if we were able to concentrate all of the heat that's generated by that curing concrete into a single oven, we could cook 500,000 loaves of bread every day for 3 years. This structure, if it was left on its own, they figure out it's going to take 125 years for it to finish shrinking and cooling down, basically. And that's not nearly quick enough. Now, the guy in charge is a fellow called Frank Crow, and they call him Hurry Up Crow, because he's a man in the Colorado River to cool my dam.
Crow embeds over 950 kilometers of steel water pipes into the concrete of the Hoover Dam. He builds a huge water chilling factory. Here he cools river water down to 4 degrees and then shoots it through the pipes into the hot concrete. This shortens the cooling time from 125 years to only 22 months.
Now, this works a treat. All they have to do is finish the dam, cement grout up the pipes, and they're out of there. Fantastic effort. It actually took 5,000 men only 21 months to build this structure. Not only that, they finished 2 years ahead of time, and they finished ahead of budget.
The Hoover Dam stores 35 billion cubic meters of water, and at the time generates more power than any other dam in the world. With this magnificent dam behind them, the cities in the American West can finally begin to thrive. The Three Gorges Dam takes concrete construction to new heights.
You look at it, you can just picture the thickness of the concrete at the base of the dam, the height of it, 180 meters, and it's 2 kilometers long. So it's a colossal amount of concrete.
Three Gorges uses 10 times more concrete than the Hoover Dam, so the engineers have to pull out all the stops to keep their dam cool.
They basically used everything in the book. They cooled the aggregates and the materials, the sands, before they put it into the mix. They added ice. They did everything they could to get the temperature down as low as they could before it started to warm up all by itself. And here, because of the issue of some of the summer weather being especially hot, July and August, they actually went so far as to use a fog spray system to blow effectively a fog blanket over the top of the dam, with the objective of blocking the solar radiation from piling down into the concrete and adding to the heat that was being generated on the inside.
Back in 1936, the Hoover Dam proved that engineers could build impossibly big concrete dams, as long as they kept them cool. But as dams grew, they held back ever more water, and with it, tremendous destructive power. To build the Grand Coulee Dam, American engineers had to protect it from the catastrophic effects of overflowing. Johnstown, Pennsylvania, 30th of May, 1889. As the town gets hit by the heaviest rainfall in its history, the tranquility of a dam reservoir is about to be shattered. It rains for 24 hours, and the water reaches the top of the dam. Soon it has nowhere to go but over the top. The dam fails, and 20 million tons of water empties in 45 minutes. A wall of water, 18 meters high, crashes down the valley and hits Johnstown. Utter destruction ensues. Over 2,200 lives are lost in the flood. It is the worst disaster the US has ever seen. Why do dams burst when they overflow? Engineer Ed McCann explains.
Now, a particular problem is when water flows over the top and weakens all of the ground in front here. They're very vulnerable to a thing called toe scour. And we're going to have a go at modelling to see if we can see what happens with toe scour. This is our flood coming along in our river, and it fills up behind the dam. We're right up at the top here now. And the water will soon start pushing over the top and coming down. And it will fall down this face and scour away underneath. And you can see the dam starting to move already. As the ground in front of it is lost, the dam loses its foundation and begins to rotate over. And it won't be too long before it goes all together. And bang. Which is a reasonably satisfactory dam failure. When it goes, we get a tremendous wall of water come down the valley. And if you happen to be down there, you're probably dead now. Well, you can see there, toe scour on this sort of dam is a huge potential problem, and it's something that absolutely has to be fixed.
In 1933, American engineers start work on the Grand Coulee Dam across the Columbia River in the northwest of America, a dam that dwarfs even the Hoover Dam. It needs 3 times more concrete and spans 3 times the distance. As the engineers complete the Grand Coulee Dam, they have to make sure that what happened in Johnstown won't happen here. Water rushing over the dam could quickly erode the riverbed and cause disaster. So the engineers formed the bottom of the dam into a concrete ramp. This sends the water shooting down the spillway into a tumbling vortex, which dissipates its energy. As the water cascades off the ramp, it loses much of its destructive power. With the ramp in place, engineers can safely run the largest hydroelectric dam in the US, a title that the Grand Coulee Dam retains to this day. The builders of the Three Gorges Dam face a similar problem. They too must make sure that their dam is not damaged by floodwater rushing through it.
Basically, the dam holds back a large volume of the water during the flood period. Here it can hold back about 22 billion cubic meters of water. And then it's released in a controlled way through this system of 46 spillway gates and these chutes that you can see below me here. The design of a spillway like this has to deal with the force of the water as it drops over 100 meters in this case here, then achieves huge velocity at the bottom of the dam.
To deflect the force of the water crashing down, the Chinese used technology similar to the Grand Coulee. As the water levels rise, engineers open a series of gates to drain the floodwater from the reservoir. But if the water fell straight down, it could undermine the foundations of the dam. So the engineers fit the spillway with concrete chutes. Unlike the Grand Coulee ramp, which is underwater, the Three Gorges chutes hurl the water into the air. Once airborne, the water breaks up into small droplets and loses much of its destructive energy. It lands over 100 meters downstream, where it can't do any damage. So now when they open their spillway gates, the Chinese have nothing to worry about. Back in 1942, the Grand Coulee showed how dams could deal with the abrasive power of floodwater. But to build a dam across the mighty Yenisei River in Russia, engineers had to find a way to stop the water while keeping the ships moving. In the 1960s, the Soviet Union wanted to upscale its industrial power. So they plan a series of gigantic dams. One of the first, the Krasnoyarsk Dam, will stretch a whole kilometer across the river Yenisei and generate 6,000 megawatts of power. But this river is also the main shipping route into Siberia and would get blocked by the dam. To keep the ships moving, engineers hatch an ingenious plan. They will build a steel trough big enough to carry a ship. Then they will push trough and ship up to the top of the dam. Here they will spin the whole contraption round and lower it back down to the river on the other side. To move the 7,000-ton load, they will use hydraulic pumps. Engineer Ed McCann employs a hot water bottle to demonstrate the principle behind hydraulic power.
Right, connected to my hot water bottle is a pipe which goes into this bit of garden hose and is connected up to this little water tank here. So let's see what happens. I'm going to lift it up by about a metre. So I've lifted it up a metre. Now the pressure in this system has gone up, but it's not gone up enough to lift this yet. So there's no movement. The hot water bottle is still squashed flat. Now I'm going to stand back here because I don't want a load of blocks on my head. So I'm lifting up. It's about 3 meters now, and you can see the concrete blocks moving very quickly now. I'm going to take it up right to the top, which is about 4 meters, and there they go. What you can see there is the amazing power and force you can get out of water under pressure. And that's what we use to lift big, heavy stuff.
The Russian engineers use liquid under pressure to lift their ship. In the walls of the chamber are powerful pumps which squeeze hydraulic fluid under immense pressure into a set of motors mounted below. These drive huge steel cogs that propel the trough along a guide rail. The motors generate so much traction that they lift the chamber from river to reservoir in only 90 minutes. When the ship lift is opened, the citizens of Krasnoyarsk turn out in droves. This mechanical marvel is the crowning glory of the biggest dam in the world. At China's Three Gorges Dam, the engineers also face a major traffic problem. Their dam sits on one of the busiest rivers in Asia.
The Yangtze is a really important waterway for navigation traffic in China, leading all the way from Shanghai, the coast, up to Yichang, all the way to Chongqing. It's been carrying about 18 million tons of freight per year.
Getting about 170 ships a day over a dam that's more than 100 meters high is a tall order for the engineers. Befitting the biggest dam on Earth, the Chinese solve it by building the biggest ship lock on Earth. Ships enter the lock at the bottom of the dam. The gates close, water floods in and lifts the ships up to the next lock. Ships must go through 5 tiers of locks to get to the top, which can take up to 4 hours. This is fine for cargo ships, but for the many passenger boats operating on the Yangtze, it's just too slow.
To provide a more efficient transit opportunity for passenger traffic, they've built this ship lift system here, which will allow boats to go through in about 36 minutes.
Unlike the ship lift at Krasnoyarsk, the one at the Three Gorges will lift ships straight up, like an elevator. And the secret of its success will lie hidden in its concrete walls. The engineers will fit a series of massive counterweights that will do most of the lifting. Sixteen 1,000-ton concrete blocks will be connected by cables to the steel trough that will carry the ship and the water it floats in. As the counterweights drop, they will hoist the trough upwards and lift the ship to the top.
This ship lift here is 113 meters high and can handle vessels up to 3,000 tons. It'll make it the largest in the world and twice the size of the one at Krasnoyarsk. Certainly when you look at the structure now, it's got a ways to go in terms of construction. It won't be finished till 2015, but it's clearly huge. It's another very impressive achievement underway here.
After 130 years of innovation, dams have produced ever more power. Today, there is hardly a form of energy that is as clean as hydroelectric power. But as dams grow bigger, so does their impact on the environment. In their design of the Three Gorges Dam, Chinese engineers have to make sure that their structure doesn't completely block nature's way of feeding the land. The Three Gorges Dam produces more power than any other, but that's not the main reason it was built.
The Yangtze River is notorious for its really severe flooding. Over the last 2,000 years, there's been about one major flood every 10 years. In 1931, there was a really bad one, killed about 135,000 people, destroyed almost 2 million homes. And so this is the main reason why they've built the Three Gorges Dam, is to control this terrible flooding problem.
The dam blocks the path of the destructive floodwater. The water is stored in its reservoir and is then released in a controlled way. But managing floodwater can also have serious environmental side effects, as recent history has shown. In 1970, Egyptian engineers built the Aswan High Dam across the River Nile to control flooding. But soon, farmers downstream noticed that their harvests are beginning to fail. Their soil becomes so barren that the farmers need millions of tons of fertilizer every year to nourish their crops. Their land has suffered because it has been deprived of floodwater, which carries with it the vital building blocks of life. Chemist Dr. Andrew Shidlow demonstrates.
So we have here our clean rainwater, which has been falling. We're adding to it some good quality topsoil. We then add some animal excrements. We have some snail shells, essentially made of calcium carbonate. Then we have some dried leaves, plant vegetation here, and of course, fish. As the storm proceeds, as the water starts to flow rapidly, all of these ingredients get mashed up in the hugely violent storm waters which occur. So here we have it, a veritable cocktail of Mother Nature's most important plant nutrients: nitrogen, phosphorus, calcium, magnesium, and potassium.
But if floodwater stops flowing, these nutritious particles of silt will begin to settle. This is a big problem, especially at the biggest dam in the world. The flow of precious Yangtze silt is blocked by the dam and trapped in the slow-moving water of the reservoir. It rapidly sinks to the bottom where it builds up.
The silting problem on the Yangtze is a huge problem. The total amount coming down is about 500 million tons per year, which equates to about 1 kilometer cube. Perhaps enough to fill big sports stadiums hundreds of times. It's a huge amount of silt.
If this silt remains trapped behind the dam, it would mean that farmers, fishermen, and wildlife would be deprived of nutrients in the water for hundreds of miles downstream. And the tons of settled silt or sediment could build up in the reservoir and threaten the dam itself.
Basically, sediment falling into the reservoir here would reduce the capacity, the reservoir capacity, and would eventually perhaps interfere with the ability to run the turbines if it came up that high.
Cleverly, the Chinese engineers exploit the power of floodwater to flush the sediment out of the reservoir and send it downstream. They installed sluice gates deep inside the dam. Each gate weighs as much as a bus and needs a powerful hydraulic piston to lift it up. When the operators open the gates, floodwater rushes over the trapped sediment and sweeps it through the dam. This way, the Chinese authorities hope that it will be at least another 100 years before the buildup of sediment affects power production at the dam. But even the clever purging system cannot carry all the sediment across the dam. Scientific estimates on how much sediment remains behind vary from as little as 30% to as much as 60%. But the Chinese authorities believe that this is a price worth paying. They are convinced that the benefits of the dam, such as clean energy and flood control, far outweigh its significant drawbacks. As the Three Gorges project draws to completion, its scale is breathtaking. Even with some of its turbines still to be switched on, it produces more power than any other dam in the world. Standing on the shoulders of historic engineering giants, the Three Gorges really is the ultimate hydroelectric dam, until someone builds an even bigger one.